Today we're going to be graphing the primary trig functions, which you've done before in degrees, but now we're going to graph them using radians as our independent variable. So let's figure out how we can create the graphs of these functions using our special triangles and the unit circles. So first of all, let's look at the pi over 4 triangle, which we used to call the 45-degree triangle. That's this one here. We need that. We need the pi over 6, pi over 3, which is the 60-30 triangle. We need that one. And we need the unit circle. So the unit circle, I'm just going to add a few things on here. We've got our x-axis here. Starting from a positive x-axis rotation, we rotate around. This is 90 degrees, which now instead of 90 degrees, we're going to call that pi over 2. So I'm going to label at the top of my y-axis here, that's pi over 2. And then going down to the other part of the x-axis, that's pi, which was our 180 degrees. Down at the bottom is 3 pi over 2. So we started at 0 radians, or a full rotation is 2 pi radians. So those are the coordinates that you see there that match those radian measures. Using these references, we're going to fill in this chart without a calculator. So sine of 0, sine of 0. What is sine of 0? So if you don't know this one, we don't have 0 anywhere except here. The unit circle has 0 right there. There's our 0. Sine of 0 radians. Remember that sine is the same as the y value. So we have right here this coordinate. The 1 is an x. That's an x, and the 0 is a y. So sine of y is going to be, let me circle that, our y value is 0, so sine of 0 is 0. Sine of pi over 6, okay, we look at our pi over 6 angle here. Sine is opposite over hypotenuse, 1 over 2. So sine of pi over 6 is 1 over 2, or you could write 0.5 if you want, but we're going to stick with exact values here, 1 over 2. Sine of pi over 4, look at the pi over 4 triangle. The pi over 4 triangle sine, you could use either angle, either corner here, because they're both pi over 4. Sine is opposite over hypotenuse, that's 1 over root 2. I'm not going to rationalize that, I'm going to leave that as 1 over root 2. And then if you just take a look off to the side here, you'll see that 1 over root 2 is approximately equal to 0.71, because we're going to have to graph these values. So it's pretty hard to graph 1 over root 2, but we can graph 0.7. Okay, pi over 3. Here's our pi over 3 angle. Sine is opposite over hypotenuse. That's root 3 over 2. Now the next one is, root 3 over 2. The next one is pi over 2. So for pi over 2, we have to go, we don't have a pi over 2 triangle, but we're going to go right here's our pi over 2. Sine means you look at the y value of the coordinate, and the y value is a 1. So sine of pi over 2 is 1. Now 2 pi over 3. So how do we do 2 pi over 3? We don't have a 2 pi over 3 triangle, but we have a pi over 3 angle. So what we do is we kind of ignore, we're going to ignore the 2 for a minute. We're just going to look at the pi over 3. So sine of pi over 3, we already know that one. Sine of pi over 3 is root 3 over 2. So these are related. So I'm going to write root 3 over 2 here. It's going to be related to this answer, but we just have to figure out if it's a positive or a negative. So 2 pi over 3. 2 pi over 3. I'm going to draw a little sketch over here to the left. 2 pi over 3. What quadrant is that in? So this is pi, which is the same where you're going to use the denominator of 3. So this is 3 pi over 3. Pi is the same as 3 pi over 3. So this would be 1 pi over 3, 2 pi over 3, 3 pi over 3. So 2 pi over 3 is in quadrant 2. I'll put a 2 down here as well. 2 pi over 3 is in quadrant 2. So 2 pi over 3 in quadrant 2 is sine positive or negative in quadrant 2. quadrant 2 is sine positive or negative. It's positive. So sine of 2 pi over 3 is going to be root 3 over 2. It's going to be positive. 3 pi over 4 is also in quadrant 2. So you're thinking, ignore this 3 for a minute. You're looking at pi over 4. Pi over 4, we already know pi over 4 is 1 over root 2. Sine of pi over 4 is 1 over root 2. And sine in quadrant 2 is positive. So I'm not going to change that to a negative. Next one, pi over 6, 5 pi over 6. So 5 pi over 6, going back up to my grid here, I'm just going to change this to blue here. This is 6 pi over 6. 6 pi over 6, so we have halfway would be 3 pi over 6, that would be our 90 degree. We've got 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi, 5 pi, 6 pi. So 5 pi over 6 is also in quadrant 2. And pi over 6 we already know from before. Pi over 6 is over here. We already have pi over 6 from before. So I already know that it's going to be 1/2. 1/2. And in quadrant 2 is sine positive or negative. It's positive, so it stays 1/2. Next one, pi. Sine of pi. So I'm going up here to my unit circle. Sine of pi, I have an x value and a y value. Sine is y. So the y value is 0. 7 pi over 6. 7 pi over 6 is going to be down, looking over here on the left. Remember 6 pi over 6 was here. So 7 pi over 6 is obviously just one more sixth past that. So 7 pi over 6 is in quadrant 3. So we'll put a 3 here. All of these, from looking at the unit circle, anything from pi to 3 pi over 2, anything in this quadrant is in quadrant 3. So here's pi, I put a check mark, here's pi. 3 pi over 2 is here, so everything in between is going to be in quadrant 3. These are all quadrant 3. So in quadrant 3, sine is negative. So in quadrant 3, we need all these to be negative. So we just go back to our original numbers. Pi, ignore the 7, so I'm looking at 7 pi over 6, ignore the 7. Pi over 6 was 1/2. But in quadrant 3, that's got to be a negative 1/2. So 7 pi over 6 is negative 1/2. 5 pi over 4, ignore the 5. Pi over 4 was, looking back on our chart, was 1 over root 2. And in quadrant 3, that's negative. 4 pi over 3 is going to be negative root 3 over 2. 3 pi over 2. 3 pi over 2 is down at the bottom here. That's 3 pi over 2. That's 270 degrees. Sine is the y value, which is -1. So -1. 5 pi over 3. Everything up until 2 pi, I'm looking at the last quadrant here. Anything in here is quadrant 4. So anything from 3 pi over 2 to 2 pi is quadrant 4. So in quadrant 4, sine is also negative. So all of our answers are going to be negative here. Negative. So I want you to press pause and fill in this chart yourself and then come back and look at the answers. So there's the rest of your chart, and we did this in grade 11, except everything up here, our independent variable was degrees, and these were all just degree equivalents, and we used them to graph the sine wave. So we're going to graph it now. We're going to use intervals, theta intervals of pi over 6, but we're only going to graph the easy points. So what I mean by that is, I'm like this one right here, pi over 4 and 1 over root 2. That's kind of hard to graph. I'll show you what I mean. So let's get our axes on there. There's a y-axis and there's the x-axis. So we're just going to label intervals of pi over 6. So this is where you have to get good with your fractions, right? So I'm going to count by sixths. So this is going to be 1/6, which is pi over 6, 2/6, which is the same as a third, 3/6, 4/6, 5. So I'm not going to label every single one. Let me just put them on here. The first one would be pi over 6, but I'm going to do, that would be pi over 6. That'd be 1/6, 2/6, 3/6. So I'm going to do the 3/6, which I will reduce to pi over 2. 3/6, 4/6, 5/6, 6/6, that's pi. 7/6, 8/6, 9/6 is 3 pi over 2. 9, 10, 11, 12/6 is 2 pi. So what I've done is I've taken the unit circle values here, pi over 2, pi, 3 pi over 2, and 0 and 2 pi. So I've just taken these ones that are in black and I've spread them out here in pi over 6 intervals. So I could keep going, but that's all I'm going to put. I'm just going to do a little bit on the negative side of the axis as well. So my first grid line would be negative pi over 6, negative 2 pi over 6, negative 3 pi over 6. So negative 3 pi over 6 is negative pi over 2. And then negative 4, negative 5, negative 6 over 6 is negative pi. Negative 7, negative 8, negative 9 pi over 6 is negative 3 pi over 2. Negative 10, negative 11, negative 12 pi over 6 is negative 2 pi. So there's my theta axis. I'm putting a theta here. It's okay if you put an x because we're so used to that being the x-axis. It's okay whichever one you put. Okay, so that's what I mean by kind of the easy points. I'm not going to do all of them. Now we're going to use y intervals of 0.5 just for the graph that I have. Even though if I look for my maximum value, what's the maximum y? This is my y here. My maximum y value, if you don't know, you might have to put √3/2 in your calculator to see what it is. But my maximum y value is 1. So that's my maximum is a 1 and my minimum is a negative 1. So my maximum is a 1 and my minimum is a negative 1. So I can use intervals of a half and go up the y-axis. This is 1 and this is negative 1 and that's my y-axis. Okay, now we are going to graph. So let's start with, first of all, our first coordinate is that we got. It was 0, 0. That's going to go right there. 0, 0. 0, 0. Put a dot there. And my next coordinate is, so I could do pi over 6 and 1/2. That would be right here. And we're not going to graph them all because there are so many and they're hard. When we get to pi over 4 and 1/2, that's a little harder to graph. So I'm only going to graph the easy ones here. Let me just highlight them. So I'm going to graph 0. I'm going to graph pi over 2 and 1, pi and 0, 3 pi over 2 and negative 1, and 2 pi and 0. And you can certainly put any of the other points you want to get a better graph. But we really only need the maxes, the mins, and the the equation of the axis, the intersection with the equation of the axis. So pi over 2 and 1, I'm putting that one on. Pi and 0, 3 pi over 2 and negative 1, and 2 pi and 0. So what I have here is a nice wave. So I find it difficult to graph, to draw a wave nicely. I'm starting from one point and going right to the end. I usually like to go to a maximum. So I'm going to start at the pi over 2 maximum and I'm going to just go, it's almost like I'm creating a parabola here. I'm doing kind of a concave down curve there. And then I stop. And then I go to a minimum and I do like an opening up parabola or a concave up parabola curve here. So that's the way I find it easier for me to draw waves rather than just trying to connect the dots. To get the rest of the wave, I'm going to use symmetry. I can tell that from the origin here, obviously my wave's not going to come back up again, it's going to come down. So I'm going to be negative pi over 2. So I'm going to put a dot here. a dot here and here and here. There. And then I'm going to do the same thing. I'm going to start at a maximum to draw my wave, half of it at a time, back down to the bottom. Oops. And I'm going to put arrows on the ends because this continues on to infinity, up and down onto infinity. So there's the sine wave graphed in radians for our theta axis. What is the period? The period means how, what is the horizontal distance, how many units before it repeats itself, and it's one full cycle, right? That's 2 pi, because once we get around the circle once to 2 pi, then we just start repeating ourselves again. So the period is 2 pi, and if you remember from degrees, that was 360 degrees. Period is 2 pi. The theta, or the x-intercepts, those are here, all of these, and there's an infinite number of them. In your homework, you have to summarize where they all occur. You have to get a kind of a general formula. We did that way back in chapter 1, so you can look that up again if you want to, but the ones that we see here, I'm just going to list the ones that we have on our graph. We have negative 2 pi, pi, 0, sorry, negative pi, positive pi, and positive 2 pi. So those are the theta intercepts that are on our graph. But again, you do have to use a repeating, you will have to use a repeating pattern, I think, for that later. Equation of the axis. The equation of the axis is the horizontal line that cuts our graph in half. And since we haven't shifted it up or down at all, the equation of the axis is just y equals 0. Y equals 0. The domain, as you can see, it continues on to infinity. So x, or theta, I'll put theta here, theta is an element of real numbers, and there's no such that. Theta can be anything. The range is y is an element of real numbers, and we already talked about that when we looked at our max and min over here. We already talked about the range. The lowest value is a -1, which is less than or equal to y, which is less than or equal to 1. Remember, with range, you always put your low number first and then your high number after that. So you've just graphed the sine wave using radians and not using your calculator. Now let's try cos. We're going to do some fewer points this time. We're still going to use this domain 0 to 2 pi to get one set of points, and then we can extend the wave after we have one wave. We can draw as many waves using symmetry as we want from there. So cos theta, cos of 0. So think back to your unit circle. Cos of 0. So I'll draw a little unit circle over here. Cos of 0, let's pretend that's straight. Here's 0, here's pi over 2, pi, 3 pi over 2, and then back at 2 pi. Cos of 0, here's my coordinate, I'm putting a dot right here. The coordinate there is, what is the coordinate there? It is 1, 0. Cos is x, so cos of 0 is 1. Cos of pi over 4, you go back to your special triangle. Pi over 4, cos is adjacent over hypotenuse, so that's going to be 1 over root 2. Pi over 2 is up here on the circle again. Pi over 2, the coordinate there at pi over 2 is 0, 1. So the x value is a 0. 3 pi over 4, so ignore this 3. Look at the 4. We've got pi over 4 for a denominator, so we're ignoring the 3. Pi over 4 we already know is 1 over root 2. 3 pi over 4 is in quadrant 2. In quadrant 2 is cos positive or negative. It's negative. So we're going to, 3 pi over 4 is going to be negative. Pi's right here. What is the x value right there? -1. 5 pi over 4. So we know that pi over 4 is 1 over root 2, but 5 pi over 4 is in quadrant 3, and in quadrant 3 cos is negative. 3 pi over 2. 3 pi over 2 is down here. What is the x value right here? It's 0. 7 pi over 4. So it's a pi over 4, which means it's going to be 1 over root 2. Now you just have to think if it's positive or negative. What quadrant is that in? 7 pi over 4 is going to be positive because it's in quadrant 4. And then 2 pi is back to where we started at 1. The maximum value we have is 1. The minimum is -1. The period. So the way you calculate period, just a reminder of the formula, the period is 2 pi divided by, it used to be 360 divided by k, right? And you always use a positive. Those absolute value markers are showing you it's got to be a positive. Even if your k is negative, you put a positive there. So our period is what used to be 360 divided by k. It's now 2 pi divided by k. Up in our equation, the k would be right in between the word cos and the theta, so it's an invisible 1. So the period is 2 pi. The theta intercepts, so the ones we haven't graphed it yet, but the ones that we have according to our graph are, here's an intercept, and here's an intercept. Those are our theta intercepts. Let me just put them on the graph. Pi over 2 and 0. There's one. And 3 pi over 2 and 0. So those are our theta intercepts. We have them at pi over 2. And in your homework, I believe you also have to state all of the theta intercepts or all of the x-intercepts. So you're going to go back to reviewing how to use that arithmetic formula Tn equals a plus n minus 1d to solve for the intercepts. The equation of the axis, that's your halfway line. Well, let's do the graph. We don't need the graph to figure this out, but since we're just starting out, we will put it on. So my first coordinate is 0, 1. I already have a scale on there. That makes it a little faster. 0, 1. I've got the pi over 2, pi and -1. And the last point I'm going to put on is 2 pi and 1. And now I'm going to draw my wave here. Again, I just start with a max or a min. I don't like that one. I just start with a max or a min and try to think of just drawing a concave up or a concave down portion. And it does continue on. Equation of the axis, that's the halfway line. It's the same as it was for sine, y equals 0. Domain is also the same as it was for sine. Theta, we use theta, is an element of all real numbers. And the range is the same as that was for the sine wave as well. I'll just put it below here. The range is y is an element of real numbers such that, now we put our low number first. We put our less than or equal to, don't turn those around and make them greater than, and our max is a 1. So of course the cos wave is very similar to the sine wave, it's just a shift of it really. They're identical in many, many ways. But the tan wave, and some of you may never have graphed tan before, even using degrees. So we're going to take a look at this and we're going to try to understand why tan looks the way it does. So we're going to talk a little bit more about its values. So tan is sine over cos. That's the definition of tan, or y over x. So what you need to do is look back, if you've been keeping notes here. I want you to look at what you had for sine of 0 and what you had for cos of 0. And when we divide them, that will be our answer for tan. So sine of 0 is 0. Cos of 0 was 1. That means tan of 0 is 0 divided by 1 is 0. Pi over 4. Okay, pi over 4. Sine of pi over 4 was, I'll just write the decimal because I don't have a lot of room here. I'm just going to put 0.7. over cos of pi over 4 is also 0.7. So tan of pi over 4 is 1. Next one, pi over 2. So look at what you had for sine of pi over 2. Sine of pi over 2 was 1. Cos of pi over 2 was 0. So tan of pi over 2 is going to be, I'm going to put a U here for undefined. We're going to have an asymptote there. I want you to fill in the rest of the chart, press pause, and then when you're done, see if it matches what I've got. All right, you've got this chart done here. Before we start to fill in all this information, let's go over and graph it. So I'm going to start with everywhere I have a U for undefined, I'm going to draw in a vertical asymptote. So let's talk about these vertical asymptotes for a minute here. I've got one at pi over 2 and 3 pi over 2. From that, can you deduce or can you figure out where the other ones would be? Because we've got a big grid here. So I would have more vertical asymptotes. Where would they be? So let's maybe use this time to talk about that little arithmetic formula, sequence formula here. We're going to figure out where all of the vertical asymptotes are. So the formula, will I be able to fit it here? Let's see. Okay, the nth term, the general term, a first term plus n minus 1 times d. So I'm going to come up with a general formula to show where all of the vertical asymptotes are. My first one, A stands for my first one. Usually you can pick anything because these are infinite, but I'm going to use the first positive asymptote I have, which is a pi over 2. That's the location of my first vertical asymptote. N stays n, Tn, and d is the common difference. So what is a common difference between these two asymptotes? How many units are in between there? And the answer is pi. So there's a total of pi units there. So 3 pi over 2 subtract pi over 2 is the same as 3 over 2 subtract 1 over 2. So our common difference is pi. So I'll put a pi there. And then I'm going to distribute that pi backwards into the bracket. And I'll have Tn equals pi over 2 plus, I can put pi n or n pi, it doesn't really matter which way you put it, n pi minus pi. We have some like terms here. We have, so ignore the pi if you want to think of it as an x. This is like 1/2 minus 1. So what's 1/2 minus 1? I'm running out of room, so let me just move it up a little bit here. 1/2 minus 1 is -1/2. So -1/2 I write as, but it's a pi, negative pi over 2 plus n pi. So that's n pi. That's a formula to show where all of the vertical asymptotes are, and n is an element of integers. So I can only sub in 1, 2, 3, 4, 5, -7, -3. I can't sub in decimals or fractions. So that is a formula. Now the back of the book sometimes uses a different value for a. They might take, instead of the first positive, they might take the first negative, and so their formula will be different. But this is a formula for all of the vertical asymptotes. So when we get to the domain is going to be x is an element of real numbers such that x cannot equal, and then I'm just going to write this thing out here because it can't equal any of those locations. There are other ways to write, there are other ways to write the formula too. So again, if the back of the book is different, or if you came up with one on your own, which is certainly possible, you can see a pattern right here and you can say, well, I'm going to write a little formula here. I can see one. Then go ahead and do that. But you can see where they should be. They're occurring every pi units. So there's going to be another vertical asymptote here and another one here. So I'm going to go ahead and draw those in as well. All right, so there are our vertical asymptotes all drawn in there, the ones that we can fit. The next thing we want to put on are the points we have. We don't have too many, so 0, 0. That's a pretty easy one to put on there. We've got 0, 0. The next one we have is pi over 4 and 1. So pi over 4, so that's like a quarter. A quarter is halfway between 0 and a half. So I'm going to go halfway on my x-axis between 0 and a half. And that's kind of awkward to put in there, but do our best guess here. It's about 2.5 lines over, and 1. So there's 1 point. The next one on our chart that we have is the asymptote. We already put that on. So we have 0, 0, pi over 4 and 1, pi over 2 and undefined, 3 pi over 4 and negative 1. 3 pi over 4 is halfway between pi over, so it's 3/4. 3/4 is halfway between half and a whole. So 3 pi over 4 and negative 1. So this is looking really strange. I'm going to put a dot right about there. And then my next one on my chart is pi and 0. Let's put a dot there. And the next one is 5 pi over 4 and negative 1. Oops, sorry, 5 pi over 4 and 1. Out there. We're almost at the end. Then our asymptote, then 7 pi over 4 and negative 1. And then we have the last one that we found with our chart is 2 pi and 0. Okay, how do we possibly come up with a graph out of this thing here? The one thing we can do is we can look at the end behavior as we approach the asymptotes. So I could sub in a number really, really close to pi over 2 on the left side of it, and I would see, and yeah, we have to do this later, so I'm not going to spend a lot of time on it today, but I would see I'm getting a number positive infinity here. So my graph is going up here. On the other side of pi over 2, a number just on the other side of pi over 2, if I sub that in, I would be way down here. So what's happening is this section here is the only one I have a full segment of. I'm going to draw a wave like this. That's what the shape is going to be in there. It's almost like a cubic. It's got that little kind of a cubic shape like that. So let's try to put that in. Again, I'm going to start at the intercept at pi, and I'm going to go concave up. So I'm going to curve up here, and my line's going to keep erasing because my tablet doesn't really like what I'm doing. Yeah, I knew that would happen. And then on the other side of pi, I'm going to go concave down. Oops, I should be passing through that point though. So remember that we can never ever cross vertical asymptotes, although we can sometimes cross horizontal asymptotes. We won't cross this vertical asymptote. We're going to use symmetry to do the exact this piece that we have drawn. We've drawn one full cycle right here. In between the two asymptotes, this is one cycle of the tan graph. And I'm just, if I had like a stamp, you know, that you stamp it in ink, I would get the same thing here, and the same thing here, and the same thing here. It's just over and over and over again. So we're just going to do a few more pieces here and here, and then we'll finish up all of our data on the side. So there's what, it's a little shaky looking, but that is the tan function. That's what the tan function looks like. Let's talk first about its period. What is the period? What is one full cycle? How many x units, how many independent units do we have before we start repeating ourselves? So remember, we originally started with just this one section here. So that is pi. The period is pi. It's a width. The period, the cycle, is pi units. So period is pi. What about the maximum and the minimum? There are no maxes and no mins. None. And the theta intercepts, yes, we have lots of those. We have an infinite number of those. I'm just going to list a few of them that we have here. We've got 2 pi, sorry, negative 2 pi, negative pi, 0, pi, and 2 pi. But you can come up with a repeating pattern for all that. Obviously, it occurs every pi. Every pi units, we have a theta intercept. Equation of the axis, that again, same as sine and cos, is y equals 0. That's our halfway line, kind of. The domain, we talked about this already. Domain is x or theta is I'll use x this time. X is an element of real numbers such that we can't have any of those vertical asymptotes. So such that x cannot equal, and I'm going to write this in here, x cannot equal negative pi over 2 plus n pi. So those are our vertical asymptotes. Other than that, we can use any x value. The range, unlike sine and cos, the range for sine and cos, y is an element of real numbers. For sine and cos, we had a minimum and a maximum. For tan, we do not. It's just y is an element of real numbers. So that's the graph of tan. You have some questions that say, using graphing technology, please use Desmos. And if you've forgotten how to get these repetitive patterns, this kind of thing that I did up here, then you've got to go back and look it up in your notes. When you're using Desmos, make sure you follow these steps here and set it to pi. So see how I have my x-axis is showing up in pi's and pi over 2? You can get, Desmos can do that for you. You might have to type a pi, or you can just use the pi symbol on the Desmos keyboard and make sure it's in radians and not degrees. So those are just some tips to help you with your homework, and that's what you're working on today, are the graphs of the primary trig functions. That's sine, cos, and tan. Cosecant, secant, and cotan are secondary, so these are just our primary ones that you're working on today.